Today we're going to take a look at autoencoders, and then after the break a more general view of representation learning and transfer learning. We're going to start by looking at what are autoencoders, the motivation and the principles, and then looking at different ways of restricting the way the network learns in order to obtain better encodings. So we're going to look at undercomplete autoencoders, which are the more intuitive, and then different types of regularization to try to obtain more useful encodings. And I'm going to talk a bit about applications to dimensionality reduction and similar. So the first thing that we're going to look at is the idea behind an autoencoder. Basically, we are going to train a deep network to output the same thing that we input into the network. So in this sense, we can say that this is unsupervised learning, because even though from the mechanics of the network, we are still minimizing a loss function, doing backpropagation, and measuring the error at each mini batch in order to minimize that loss function. So it works exactly like supervised learning. There is no difference here. We are training the network without the need for additional labels. So as long as we have a data set, even if it's unlabeled, we can train an autoencoder. So from our perspective, it's like unsupervised learning. And the idea here is that even though the network is not doing anything useful, because we put in an image of a cat and we get out the same image of the same cat, ideally, what we are interested in is what happens inside the network. So remember that the way the deep learning works is that we are training a deep neural network to create different representations of the data along the different layers in order to fulfill some purpose. For example, classification, regression, those examples that we saw before. In this case, the purpose will be to create this encoding. So we can think of the first half of our autoencoder as the encoder part, which will convert the input into some latent representation here in this hidden layer in the middle, and then the network will be able to reconstruct the original input from this representation. So basically what we are doing here is we are coupling the encoder and the decoder. This is why it's called the autoencoder. We are automatically encoding and decoding the same thing at once. But what we want to do is to map from our input space into some latent space where the representations of all these cat images will lie, in a way that it makes it possible to retrieve the original images in the decoder. So this can make it so that the latent space representation is useful and captures important aspects of the data that we have. So in this case, we are merely creating a network that will approximate this composition of two functions. So the encoder part with this fx maps the input into the latent space, that hidden representation, and then the decoder maps it back into the input. So basically we are learning a composition of functions that return exactly the same thing that we are inputting into the functions. So this would not be interesting by itself, because note that this has a trivial solution, which is simply copying the values. If the network learned to copy the same values from one end to the other, it would solve this problem. But what we can do is include some constraint that does not allow the network simply to copy the results. And this can, as long as we force the autoencoder to do something useful with the data, it can help us learn these representations, lowering dimensions, capturing important features, structuring the data, and so on. So the idea here is that even though the autoencoder can be trained with the same algorithm that we used for supervised learning, from our perspective, this is unsupervised learning because we don't need to label anything. We just need the X values. We don't need those labels. And so this is potentially very useful because generally we have a lot more data than labeled examples. We just need to force the autoencoder to give us some useful representation. In other words, we need to prevent it from merely copying the values from one layer to the next. So let's see one example. This example that I showed in that image was an undercomplete autoencoder. An autoencoder is undercomplete if the dimension of the hidden representation, this latent space, is smaller than the dimension of the input. For example, in this image here, you can see that we have a number of values in the input. This could be all the pixels in the image. And then in the hidden layer, we have fewer neurons. This means that a large set of values must be encoded in a smaller set of values in a way that allows for the original data to be retrieved. So this would be an undercomplete autoencoder, and these are very easy to understand intuitively because we are now minimizing a loss function that simply penalizes the difference between the output of the network, which is the composition of the encoder and then the decoder, and the difference between this output and the input x. So we just use this as a loss function, for example, binary cross entropy or minimizing the quadratic error, something like that, and we try to match the output to the input. If we just use a linear transformation, this will be similar to PCA. Of course, PCA also has this orthogonality constraint where the different directions must be perpendicular, but it would be the same idea. With nonlinear transformations, an undercomplete autoencoder can find much better representations of the manifold in which the data is distributed. Of course, we cannot use a too powerful an autoencoder because then we can make it so that all the information necessary for recreating the input is stored in the weights of the decoder. And so in an extreme case, the encoding could just give an index. So this is example number 1, this is example number 2, and so on. And the decoder would know what example number 1 looks like, example number 2, and so it would not learn anything useful. So one thing that we need to take into account here is that even though we are training the network in a way that, from our perspective, seems like unsupervised learning, remember that from the perspective of the network, we still have the same kind of training, which is minimizing that loss function. And we are also concerned about the problem of generalization, because if our network loses the ability to generalize from the training set, it means that it's not adequately capturing the structure in the data. It's just memorizing what each example in the input corresponds to when it needs to recreate the output. So even though this is unsupervised learning, it is useful to control for overfitting and use, for example, a validation set. This is a classical example, Mitchell's autoencoder. I already talked about this in other lectures and also mentioned this in the machine learning course. But the idea here is that we have combinations of zeros and ones, 8 different combinations. We can imagine this to be a one-hot encoding of 8 different possible values. And this is fed into the input of the autoencoder, which has 8 inputs. The hidden layer is just one hidden layer, has only 3 neurons. And then we have an output layer with 8 neurons again, which we train to recreate the input. And so what we find is that we are converting this input in 8 dimensions into an input with only 3 dimensions, only 3 neurons here. And this will create a binary representation of the 8 different combinations. So you can see here the 8 different combinations of 3, 0, 1 values. So this one use of autoencoders, especially undercomplete autoencoders, is to learn the manifold in which the data is distributed. A manifold is a set of points that in the neighborhood of each point is similar to a Euclidean space, so can be mapped to a Euclidean space, but is embedded in a higher dimensional space. For example, we have here the points at the surface of a sphere. These are the coordinates of seismic events. And even though they are distributed in 3 dimensions in the surface of the sphere, at each point we can approximate this to a 2-dimensional Euclidean space, for example, a local map where we have the seismic events. So we could find a representation, a 2-dimensional representation that would approximate this distribution of the data. And we can do that, for example, converting the coordinates into latitude and longitude, and then we can use this 2-dimensional representation of the data. Note that this mapping between higher dimensions and lower dimensions needs only to be local, so in the neighborhood of each point. If you try to represent the surface of a sphere on a 2-dimensional map, you will have problems with very large distances, and you'll have the edges of the map and so on. But close to each point, you can make a map that is quite accurate. So this we can use to find a lower dimensional representation of the space, of the data distributed in that space. For example, this data set is distributed along a line, and we could, in theory, map this to a single dimension without losing much information about the relative positions of neighboring points. So we saw in the machine learning course, those of you who had the machine learning course last semester saw some algorithms for doing these manifold learning, and one of the ways we can do this is using autoencoders. So using PCA is not very good. Linear transformations may not be able to capture the structure of the data adequately, but if we use an autoencoder, we can create a transformation from the higher dimensional input data into a lower dimensional representation with an undercomplete autoencoder that better captures the way the data is distributed in that lower dimensional manifold. So this is a comparison using the banknote dataset that separates true real banknotes and fake banknotes. And if we use a principal component analysis, this is only a linear transformation that tries to preserve as much as possible the variance in the data by going from the original 4 features, so 4-dimensional space, into 2 dimensionals to plot this graph. We see that there is still a very large overlap between the 2 classes. But if we train an autoencoder, for example, this is an autoencoder with 6 for 2 and then for 6 neurons. So we input the 4 features into 6 neurons, then we reduce to 4, 2, then we expand to 4, 6, and then we have an additional layer with 4 neurons for the output, so that we can recover exactly the same input that we inserted into the network. But then what we use is only this first part to project the original data into 2 dimensions, and we have this result here. So this captures a lot better the structure of the data and gives us a better separation in this case between the 2 classes. So the reason why this works, manifold learning with autoencoders, is because we are forcing the network to do 2 different things. First, reconstruct the input as accurately as possible, but also meet some constraints that we are imposing. For example, in undercomplete autoencoders, we are forcing the network to reconstruct the input from a lower dimensional representation, which the first part of the network is learning. Now here we must be careful of overfitting, because if the autoencoder is too powerful, it can reconstruct the data very accurately in the training set, but may not be actually capturing a meaningful structure of the data. And we can see that when we try to reconstruct an example outside the training set, and we see that the error goes up. So you can optimize your autoencoders by looking at overfitting with a validation set the same way we've been doing in the context of classification, regression, and so on. Other ways of restricting what representations the autoencoder learns is to use regularization. There are different ways of using regularization, but we can even use an overcomplete autoencoder. This would be the opposite of the undercomplete autoencoder, which may have a hidden space representation, this latent representation, larger than the input and the output. So this would be a bad idea if you don't do anything else, because this will make it trivial for the network to simply copy the values from one end to the other and not learn anything useful. But if we constrain the way the network is learning by regularization, we can force the autoencoder to learn something useful because of the way we are constraining it. I'm going to give some examples. This is one example, the sparse autoencoder, in which we are forcing the hidden layer with the latent representation to have a small number of activations for each example that we presented. So the idea is that we have a lot of neurons here, but each time we present an example, we only want a few of them to be firing. For example, 5% of them. So even though we can have 100 neurons, for each example, only 5 of them on average will be firing. This will give us a sparse representation of the data that we have. We'll know with only a few values different than 0 for the representation of each example. So this is the idea of the sparse autoencoder. We can estimate the probability of some neuron firing, neuron I firing, by averaging the activity of the neuron over a number of examples, for instance, a mini batch during training or something like that. And we want to make this as close as possible to this probability, the sparseness parameter that we set. For example, 5%, something like that, so that we force the neurons to be inactive most of the time and only fire occasionally. So we can do this by using the Kullback-Leibler divergence. We saw this before. This is a measure of the divergence of the difference, so to speak, between two distributions. And we can use this to distinguish between a Bernoulli distribution with a probability P, the probability of the neuron firing for each example, and we consider this for a batch of examples, so that would be this Bernoulli probability, and we compare this with what we are measuring in our data, so for each set of examples. And we include this as a regularization parameter in the training of the network. So this would be the reconstruction loss that we're trying to make the output of the network as similar as possible to the input, but also one regularization factor here multiplied by the divergence between what we observe to be the probability of each neuron firing and what we would like it to be, and assuming a Bernoulli distribution in this case for a lot of examples. This will make it make our network prefer to find encodings that reduce the probability of firing of each neuron in that hidden representation for each example as close as possible to the probability parameter that we are setting. So this can also be due to very small activations. If you use sigmoid activations, for example, they will not be exactly 0, but you'll have some small activations there. If you use rectified linear units for that hidden layer where we will create our encoding, then this can be really 0 activations. There are other options for regularization. For instance, we can apply L1 regularization to the activation of the neurons instead of the weights. This will also reduce and reduce the firing of the neurons at that layer and make the encoding sparser. L2 regularization, and so on. There are different ways of doing this, but the idea is that even if we have a latent representation in a large dimensional space, we are forcing it to be sparse in the sense that it will have many values at 0 and only a few of them different from 0. And the result from this is that these neurons in the latent representation will specialize in identifying features that help distinguish between the different examples and that are important to characterize the examples. This is an experiment with images of 10 by 10 pixels. We have 100 neurons here on the hidden representation, so this is not reducing the dimensionality of this representation, but with the sparsity constraint on the loss function, that regularization term, this forces the neurons in the latent representation to specialize in particular features, lines at some specific position, orientation, and so on. So this is an example for each of those neurons, an example of the 10 by 10 image normalized that would maximize the output of the neuron. So this is the kind of pattern that this particular neuron prefers, and this particular neuron, and so on. And you see that they specialize in different things, so that when we present one image, only a few of them fire, indicating which of these attributes that image will have. And this is the purpose of sparse autoencoders. This is an example from a paper that in which the authors report an empirical analysis of different sparsity penalties to introduce into the loss function. For example, this is the Kullback-Leibler divergence, student T penalty, L1, L2, and so on. And you can see this is for the Menis dataset. So you can see here, for example, when using the Kullback-Leibler divergence, neurons are specializing in identifying particular types of traces in the numbers. If we don't use this kind of penalty, we have something that does not seem to have any meaning, because we are not forcing the encoder to learn anything particularly useful. So you can see here the effect of these sparsity regularization terms that make the neurons in the latent representation specialize into different, to identify different features of the input. Another possible solution to this problem of forcing the autoencoder to learn something useful is to add noise to the input. So we saw this previously with noise as a form of regularization, because if we include random noise in the data, we are creating many different examples, and we are forcing the network not to rely too much on specific input values, because those may be affected by the random noise. This is the same idea for denoising autoencoders. We are going to present to the network as input a noisy version of each example. For instance, we can randomly switch off some of the inputs. In this case, we have an image from the Menis dataset, and some of the inputs are set at white. And now we pass this into the autoencoder, but we require the autoencoder to output the original image without noise. So the autoencoder is not learning to output exactly the same thing as we input, but learning to output the image or the input vector, the original one, without the added noise. And this is why it's called the denoising autoencoder, because it's learning to remove the noise from the data. And this forces the autoencoder to learn a representation that may be, we can combine this, for example, with an undercomplete autoencoder, and we can have a representation that is smaller than the input, but it's more robust to small variations in the input, so that noise, and it captures better the actual patterns in the data instead of focusing too much on specific details. So basically the algorithm here is simple. We have a regular autoencoder, any autoencoder that we want to use. And what we are doing is for each sample that we get from our training set, we apply some sort of corruption. For example, we can switch off some of the inputs to 0 at random with a small probability, and then we train with those examples, minimizing the difference between the output of the autoencoder and the original example before any corruption. So this way we train the autoencoder to remove that noise that we are using to corrupt the examples. Another autoencoder that also tries to create a representation that is more robust to small variations is the contractive autoencoder. This one works differently. We don't corrupt the input, but what we do is we add a regularization term to our loss function. This is the original loss function, which is just the reconstruction of the input in the output, but we also add here a small fraction of the sum of the squared gradients of the hidden layer representation, so that representation at the center, which is the one we are interested in, with respect to the inputs. So we are computing the gradient with respect to the input values. What this means is that if our representation changes too rapidly with small changes in the input, this will result in a larger penalty on this term. So the network will learn representations that are more resistant to small variations in the input, and this will tend to bring together in the latent space all the inputs that are similar to one another, since the network will try not to make too big, very large changes in the latent space representation if the inputs do not differ too much. And this is why it's called a contractive autoencoder, because this effect contracts the representation, bringing together those examples that are more alike. It also favors smaller weights, because the smaller weights will also reduce the gradient of the activation with respect to the inputs. So it serves also to reduce everything, the scale of the representation, bringing together similar examples and so on. So this is another way of making the representation, the latent representation, less sensitive to small variations in the input, and also encouraging it to learn a smoother manifold where our data will lie. So we get, in that sense, a better representation of the distribution of the data if we are not interested in many small variations due to fluctuations in the values, but just to have a better representation of the overall shape of the data. So this is related to denoising autoencoder. They tend to learn approximately the same kind of things. Denoising autoencoder discourages being too sensitive to small perturbations because of the insertion of noise, which forces the network to try to ignore these small variations. Contractive autoencoder forces the derivatives of the activation with respect to the inputs to be smaller. The disadvantage of a contractive autoencoder is that it's more expensive to compute and to train. Adding noise to the data is very inexpensive. Computing all the derivatives of the activation with respect to the inputs can be quite expensive during training. But contractive autoencoder will identify aspects of the data, or will create a representation of the data that follows more smoothly the kind of changes in the data that are meaningful in the data. So I'm not going to detail too much this representation, but the idea here is to find these principal components of the the tangents to the hypersurface where the data is being projected when we compute the manifold. So you can imagine that we are projecting this kind of images, for example, the MNIST images, into this latent representation. And now we are looking at what are the directions in which we can change and still remain in the same manifold where the data is. So we can see different changes in the zero or in this kind of images of the horse, which are capturing aspects of the image. If we compare this to what would happen if we try to do the same visualization with the principal component analysis, for example, then those tangent directions to the manifold projection are really not very meaningful. So the shape of the manifold is not as good. It's not as representative of what the data is like in this particular case. But anyway, it's not the details of the visualization are not very important. The important thing is to understand this additional power of the autoencoder, which is learning nonlinear transformations, and the effect of minimizing the gradient of the activation of the neurons that are giving us the latent representation with respect to the inputs, so that we are forcing the representation to follow this hypersurface that better matches the actual distribution of the data. And so the directions where it can slide on the tangent vectors to this hypersurface will have some meaning in the original data. We can also use autoencoders to learn probability distributions or the parameters of probability distributions. We also used, for example, the softmax layer to learn a probability distribution for each point of belonging to one class or the other, and so on. So the way we can do this in an autoencoder is to use the encoder to give us the conditional probabilities of some distribution in the encoding given the data. So the encoder will try to create this probability distribution for each example that we present, and then the decoder will, given those parameters, try to output, or that probability distribution for the encoding, try to output a set of values that is as close as possible to the input. So we can do this to output values from representations in some particular distribution. This is analogous to what we did, for example, using the sigmoid to model the probability between 0 and 1 when we are using classification between two classes, or the softmax for the multi-class classification, or even the linear output in regression, which in effect is an estimate of the mean of that Gaussian distribution that we assume to be the source of the error in our data when we use the minimum squared error function for training. So this is the kind of thing that we've been using so far, but we can use this to generate data. And the idea here is that if we have an autoencoder, we have a mapping from the original space where we have our data into some latent space representation, and then we can use the decoder to get this back. So if we use the encoder part on one particular example in our data set, we will project that example after adequate training of the autoencoder into a specific point in the latent representation from which a meaningful example can be decoded. So this is what we can do with the regular autoencoder. If we could manage to find an example somewhere inside this latent space, we could in theory just pick the right example and produce this output. However, there is a difference here between the discriminative model, which tries to approximate a function that is a conditional probability, some output conditioned on the input. This is what we do, for example, when we use a neural network classifier to try to predict the class of an example. This will give us a probability distribution. We are trying to find this kind of function where the output of our network, the class in which we classify our example, is conditioned on the input. But we are only approximating this kind of conditional probability. Given the input, this is the output that we expect. A generative model we saw in machine learning is different because instead of computing the conditional probability of the output based on the input, it computes the joint probability of both. So we could compute the joint probability of classes and examples, for instance, when we use the naive Bayes classifier or something like that, and then we could find the conditional probabilities just by multiplying or dividing the joint probabilities by marginal probabilities, or finding, for example, the class which maximizes the joint probability or something like that, like we did in those generative models. But the idea is that now we are trying to find joint distribution and not just the conditional probabilities. With autoencoders, we need to decode from the hidden representation, so this latent representation here on the hidden layer, and we need to find this, so we have this decoder that gives us the conditional probability of going from this point to this one. So basically we have this part on the decoder, but we would need, if we wanted to generate data, we would need the probability distribution of this latent space. So you can imagine this as being a case of going from a discriminative classifier into a generative classifier, where we need the whole thing in order to be able to generate new examples. Or you can think of this in a more intuitive way, in which we can use this decoder to generate images of cats, but only if we choose points inside the manifold of this latent space representation where we have representations of cats. Because if we choose a random point anywhere, we don't know what the decoder will do, but probably will not give us a cat. So we need to know the distribution of the latent space in order to generate examples using the decoder. So one way we can do this is, instead of trying to figure out what the distribution is, because if we miss the correct spot, then we'll only get garbage, we can fix the distribution of the latent space to some known distribution that we want. So this is what the idea behind generative adversarial networks, which is to consider that the distribution of the latent space is, for example, a set of Gaussians here, of normal distributions, and we are going to sample from this and pass through the decoder and generate an image. Now, in the beginning, we have random weights on this network. So if we pick some random values here, pass through the network, then we'll have noise outside. So this will not be a cat image in the beginning. But what we can do is we are going to use this network here to generate images from random samplings of this fixed distribution for the encoded, the latent space. And we're going to train a network, a classifier, that inputs images, whether they are the images generated by this network or images in our data set, and tries to distinguish between the two. So this network, we will present a cat or an image generated by the other network, and we will train this network to figure out if it's a cat or a fake cat image. And we're going to include the performance of this classifier as a penalty in the loss function when training the generative network. So this network will be trained to try to fool the classifier, and the classifier then will be trained to learn not to be fooled by the generative network. And we're going to do this to ping pong between the two of them, and this is what is the generative adversarial networks, this system of using these networks in order to improve the generation of images that look like images in our data set. So this is one example of the evolution of these kinds of networks from 2014 to 2018 in generating images, artificial images. These people don't actually exist by using this method. So we have a network that receives noise as input, random normally distributed values here as input, and generates images from there. And we have this other network that determines if it's an image of a face or not by using a data set, a large data set of human faces. So it tries to distinguish between fake and real faces. And this will force the first network to improve the generation of images until we get this kind of result. So this is one way of solving the problem of sampling the latent representation when mapping into our space, our data space. We fix the distribution and then we train the whole network in order to be able to map from the distribution into appropriate points in our data space. The way we do this with generative adversarial networks is with the assistance of another network that will try to discriminate between the fake and real data. Another way of doing this is to use variational autoencoders. In this case, we are training the autoencoder to encode the input example into parameters of some given distribution. For example, a mixture of independent Gaussian distributions, normal distributions. This way, we are going to learn the distribution for generating examples like each of the examples in the training set. So this would be the way we're going to do this with the autoencoder. We have an additional term to our loss function, which is not only the error in reconstructing our data. So from we are trying to maximize the probability of outputting something like X from this distribution that we have in the latent representation. And this is basically, we are training the autoencoder to give us as an output something that is as similar as possible to the input based on that Z distribution, the latent representation there. But we're also adding as a penalty the Kullback-Leibler divergence between the representation, the hidden representation we are getting as a function of Z, and some probability distribution that we want Z to have. So we are forcing the variation autoencoder to keep the hidden representations close to that distribution. For example, a sum of Gaussian curves, things like that. So since we know how to sample from these distributions, we can then generate the samples of the latent space representation here and use that to with the decoder network to generate new examples. So the problem here is to train this autoencoder in order to find the parameters for these distributions. We cannot actually measure what the distribution is like easily, but we can specify that the distribution of this latent representation would be something like the sum of independent Gaussians. And we compute the parameters for those in the representation. So let's imagine this architecture where we input the image of a cat and we have this latent representation here that is computing the mean and the standard deviation of different Gaussian curves. So for example, these two circles here would be the mean and the standard deviation of one curve, and these two would be the mean and the standard deviation of a second Gaussian. If we have the mean and the standard deviation of a Gaussian curve, we can now sample at random a point from this distribution, sample another point from this distribution, and this would be the vector that we input into the decoder in order to generate something that we want to be as close as possible to the input. So what we have in our loss function is the difference between these two, and also trying to keep these approximately Gaussian and independent and so on, using the Kullback-Leibler divergence. So this is what we are going to train our autoencoder for, to give us the parameters, but for each image, give us the parameters of the Gaussian distributions from which we will need to sample to get something like the image we are inputting. Now, one problem is how we do backpropagation here, because you can imagine that if we are doing multiplications and sums and rectified linear units and so on, we can compute the gradients and backpropagate and adjust all these weights. But if we reach here, throw the dice and pick a number at random and go on from there, how can we propagate the error back through this random step in order to train the encoder? And this is where variation autoencoders get a neat trick here. So this would be a naive way of doing this. We have the encoder model. It gives us the mean and standard deviation of a Gaussian distribution. We randomly select one value, and then we feed that into the decoder. But the problem with this is that when we backpropagate the gradients, we cannot continue backpropagation here, because this was a random sample and not a function for which we can compute the derivative. So let's do this in a different way. We have the mean, we have the standard deviation, and here we compute the mean plus the standard deviation. And we multiply the standard deviation by a random value drawn from the normal distribution. So 0 mean, 1 standard deviation. And this would be the expression here. It's z is equal to the mean plus the standard deviation multiplied by this random value. Now, when we're doing backpropagation, we cannot do backpropagation on this branch because this was a random sampling. We don't have the operations that we can compute the derivatives and so on. But this doesn't matter because there are no parameters to learn on this size. This is merely injecting a scaling factor there. What we can do is propagate over here and over here by taking epsilon as a constant and the mean there and so on. These are just addition and multiplication operators, and we can propagate easily through the rest of the network. So by making this adjustment, this transformation, we can do backpropagation through the variational autoencoder, even across this step where we are taking a random sample from those distributions. And this way we can learn the parameters of these Gaussian distributions for different types of examples. And one very interesting thing with variational autoencoders is, since we are trying to force these to be independent Gaussian distributions, the variational autoencoder will tend to disentangle different aspects of the data that are actually meaningful. For example, here with the MNIST dataset, we can use a variational autoencoder to encode each example into the parameters of two Gaussian distributions. We have one here on the horizontal and one here on the vertical. And what these Gaussian distributions capture is the content of the number. So with different parameters on this part here, we can set the number to 0, 1, 2, 3, 4, and so on. And this one, the style of the number. So by changing this one, we change the style with which the number is written. And by using combinations of the two, we can write a 9 in a bolder letter, or a 1 that looks a bit more like italic or something like that. And we can combine style and content in different ways. The same thing works for faces. We can have, for example, this face here in the style of this face here, or this one. And so the faces change slightly depending on the kind of styles and content that we are combining. So this is one interesting property of variational autoencoders, that not only do they allow us to generate data because we have the probability distributions for different types of examples, but they also tend to disentangle these attributes so that we can independently adjust different aspects of the data and still get something that is meaningful. One thing that I've been showing, for example, in these examples, but I did not talk explicitly, is a convolutional autoencoder. So I've always been representing them in this way. We have dense networks and then dense networks again. But actually, when you're dealing with images, you don't use dense layers for the autoencoder. You tend to use convolutional layers. So basically, a convolutional autoencoder uses convolutions to reduce the spatial dimensions of the feature maps, generally while increasing the number of filters. So we have this latent space representation that is less dependent on the spatial distribution of the patches of the features in the images, but has encodes for a lot of features. And then we reconstruct the image by upsampling the feature maps so that we get higher and higher resolution, while usually reducing the number of filters. This is done with what some call deconvolutional layers, but this is actually a bit of a misleading name because they are convolutions too. But the idea is that we are shrinking the size of the feature maps, even if we stack more feature maps when we are going down here on the decoder, on the encoder part of the net. But when we pass to the decoder part of the net, we are doing the opposite. We are increasing the resolution of each feature map and generally reducing the number of feature maps. And this can be done in different ways, upsampling followed by convolution, or fractional stride convolution, transposed convolution, and multiple convolutions. We're going to look at these different ways, but basically upsampling and then using convolution tends to work better. If we look at a convolution in one dimension, let's say we have this x here, we are using a convolution with a kernel of 4, a window of 4, and a stride of 2. Since we are using a stride of 2, and we use padding to allow us to also compute for these positions here, we end up having an output vector that has a smaller number of values than the input vector, because we are having steps of 2 here, and so we can easily use convolutions with striding to shrink from higher dimension or a higher number of values into a smaller number of values. Alternatively, we also saw that we can use convolutions with stride 1 and then use pooling to shrink from a larger vector into a smaller vector. If we want to do the opposite, go from a smaller vector to a larger vector, we can do different things. One thing that we can do is to use transposed convolution, which is, we have the input here, and we can imagine that we are transposing the way we are doing the convolution. So instead of sliding the kernel over the input, we are sliding the kernel over the output, and we are adding these operations. So for example, here, for this vector, for this value on the y vector, we would add this weight multiplied by that input, and this weight multiplied by that input, because this is the one we get when we slide again with the stride of 2. And we do the same thing for all the values here, and while we are sliding the kernel over the output. So depending on the stride and the padding here, we can increase the number of values that we have in the output relative to what we had in the input. So this is one way of going from smaller feature maps to larger feature maps. Another way of doing this is to use these fractional stride convolutions, which you can imagine as padding with zeros the intermediate values here between the values of the input. These are the original values of the input in white, and these gray values here are zero padding that we are also putting between the input values. And then when we do a convolution with a stride of 1, we get more values in the output than we have in the input. And the reason why this is called fractional stride is because if we look at just the input values of x, it seems like we are striding in fractional values along the direction of the input, because we are not taking complete steps here. But one better way of imagining this is to imagine that we padded the input by adding these values in between with zeros. But this is generally not the best way of doing this upscaling, these upsampling operations. A better way is to just upsample the feature map using, for example, nearest neighbor interpolation or linear interpolation. That means that we are going to interpolate, not just add zeros, but interpolate between the neighbors and fill in this map with the values that are taken from the original input. And then we apply a convolution, and we have a mixture of all of these. So you can imagine, for example, if we were going from a low resolution image into a higher resolution image by doing linear interpolation, we would just get an unfocused image. We would get a higher resolution image, but the edges would all be blurred because of the interpolation. If we then apply a convolutional operation, we can train the network to learn the correct operations in order to sharpen things up again. Another way we can do this would be to just do different convolutions and then shuffle or merge all these feature maps by interlacing them like this. So this would be an alternative to do this upsampling just with convolutions. But usually the more practical way of doing this is to use an upsampling operation. So we pass from a lower size to a larger size, and then just apply a simple convolution with padding so that we sharpen the output here using those kernels. And the reason why this is better is because if you do things like transposed convolution, for example, you get these kinds of strange effects due to the overlap of the different kernels. So this happens when we use this kind of operations to upsample the feature maps when generating images, for example. You can see here that in detail these images have these strange artifacts that we can avoid if we just do first an upsampling with interpolation and then apply convolutions. So this would be the more practical way to implement and gives us the best results. So another example of solving the problem of obtaining the distribution of the latent space representation. So remember that when we want to use autoencoders to generate data, we needed to find a way to know this distribution. So the decoder can give us the correct output from given the hidden layer representation, so that latent space representation, but we need to know how to sample from that latent space representation in a meaningful way in order to generate the images or whatever data we want to generate. So in this case, what we do is we use a shared encoding. We use the same encoder to encode images, for example, from these different people, Fallon and John Oliver. Jimmy Fallon, we use this encoder, and John Oliver, we use the same encoder. So we are training the same encoder to provide this encoding. And this means that images from Jimmy Fallon and John Oliver will be mapped into the same latent space. But now we are training different decoders. One that reconstructs the original images of Jimmy Fallon from examples of Jimmy Fallon. Usually these are, we can use data augmentation techniques like deforming the image slightly and so on. So we don't need large data set for this, and we have a different decoder for John Oliver. And now we can use this to convert from one to the other, because we know how to map images of Jimmy Fallon, for example, into that shared representation, from which we can extract the John Oliver face by using the John Oliver decoder. So we can, this is how deepfakes are generated. We train a shared autoencoder that maps from both people into the same latent space representation, and we have two different decoders that map from that shared latent space representation into the different outputs that we want. Okay, so to sum up the autoencoders part, this is from the perspective of the human unsupervised learning, although looking at the network, it learns just the same way as it always learns, but we do not need labeled data. And what we are doing is basically forcing the autoencoder to reconstruct the input, but with some constraints that we impose in order to force it to create some meaningful representations. We can do this with images using convolution, so you don't need to only use dense layers, and we can use it also to generate data. As long as we solve the problem of knowing how to sample from the latent representation, we can now generate new examples of the same kind of data. We can do that with generative adversarial networks. They are not exactly autoencoders, but the idea is similar. Variational autoencoders learn these probability distributions, or we can even use tricks of sharing the encoder for different decoders, and that way generate data using the appropriate decoder after creating the latent space representations with the shared encoder. Okay, so let's take a short break. We continue at 10 minutes after 5 with the second part. See you soon.